Good morning. Thank you so much for joining us today. My name is Pauline Esalu, and I'll be moderating this live webinar. This is part 2 of our 4-session webinar series. If you haven't watched the first session, the recording is posted on the registration site, and it's available on demand. Please go back and watch it. We're super excited to have you, and as always, we welcome all feedback and comments to help us improve our future webinars. Today's session is part 2 of TensorFlow, and it will be presented by Zhenying Ling and Zhangkai Zhang from our application engineering team. In today's session, we will share tips for addressing common performance bottlenecks and optimization techniques. We will also share how to use the TPC programming tools to implement custom TPC kernels. If you attended our last session, you know the housekeeping notes, but for those of you joining us for the first time today, I will review them again. Today's session is being recorded and will be made available for later viewing. If you have any technical issues or questions, please use the chat feature to reach us. During the presentation, you can use the Q&A section to ask any questions from our experts at any time. They will respond to your questions throughout the session, but we will also allocate a few minutes at the end of the presentation for any additional questions. Now, I would like to welcome our first presenter, Zhenying.
Hello, good morning, everyone. Thanks for attending this webinar. So as Pauline mentioned, you might already know how to run your models on Habana Gaudi through the previous webinars. And you might already know how to check the performance of your current run on Gaudi. So today we will tell you how you can further improve the performance through 2 key technologies. So the first optimization strategy, we call it mixed precision. So Gaudi support the bfloat16 recipe. So we will show you how you can use this to improve your model performance. The second part, we will talk about more advanced features, so how you can write your own customer kernel to first improve the model performance. So we will show you the whole process using some real model that is computer vision in TensorFlow MobileNet V2. We will show you the demo and show you how to run this model end-to-end using the customer kernel and also combine the mixed precision enabling. So first, let's look at the first optimization strategy, the mixed precision. So I guess many of you already know what's the benefit of the mixed precision. So the mixed precision reduces the precision from FP32 to bfloat16 for Gaudi case. So this improves the computing performance and also reduces the memory usage. So it's kind of fit your, so if your model is too big to fit in FP32 precision, so you can fit it with the mixed precision because it reduces the memory usage. And for the Gaudi optimization, we offer 2 options enabling the mixed precision. One is we call the Keras way. So if you already have some Keras models running, so you might be familiar with the Keras mixed precision policy. So here we will show you an example. So we have some tutorial material you can find at the Habana AI GitHub. So right now I want to show you this tutorial on how to enable the mixed precision. This is a Jupyter example. So we also run on the Gaudi hardware. So as an overview, it will show how we enable this mixed precision in the Keras model. So let's look at this. So at the first step, you can see it just import the TensorFlow and import kernels. This is applied to all the hardware backend. So it's not Gaudi specific. So after this, you can see we load the Habana module to make the model run on Gaudi hardware. So the key sentence is here. So we load the Habana module. So after this, it will show currently we have the Habana TensorFlow 1.2, and also it show you the Habana driver versions. So the Habana HPU supports a mixed bfloat 16 and FP32. That means in your model, you can have the op partially running on bfloat 16 and partially running with FP32. So the advantage of this is it will bring up speed up without any sacrifice on the numerical stability. So this is the default Keras API. It enables the mixed precision. So for the Gaudi case, it's basically set the default, convert the default ops, some selects the numerically stable ops from FP32 to bfloat 16. So this is again the default text that is applicable to other hardware as well. So in this conversion, it will keep the computing part being computed in bfloat 16, while when you saving the tensors or variables, you still have it FP32. So that way you do not the final result you still have the FP32. So that's guarantees you have this full numerical precision. So this is the process of building the model. So if the model is too small, it usually it will be very hard to see the benefit of the mixed precision because the overhead is big. So that is the same for all the hardware. So for this particular demo, we build is a large model, so make it 256 dense layers. So in these layers, it uses ReLU to activate the network. So you can see here, you can check the type. So the model type, the layers are being running on bfloat 16. So the output, the kernel tensor, it is kept in FP32. So the last layer is the softmax. So because it's we all see with the output, normally we need to keep it in bfloat 16. So the incorrect way. So because of the default, when you define the whole layer, so it make everything in the computing part being bfloat 16. So normally we can manually change it to FP32 through specify the type for the layer. So like what you can do is in this sentence. So when you set the the data type manually specifically, it overrides the previous policy setting. So here you can see the output is really FP32. So So this kind of like converting, so in the script is normal. So you can always have the fine control. So which layer you want to run it on the bflow setting, which layer you want to run it on the FP32. Right now, so you after you set up the model, so right now you can do the compilation and also provide the input. So if the input data is processed on CPU, so for CPU, we normally make it run with the FP32 instead of bflow 16, because the bflow 16 does not benefit CPU performance that much. So this is some the initialization process, and with this input setting, right now we can run the real model. The real model just use the pre-compiled model using the fitting data. So right now, so it's you can see it's print out all those kind of see some, yeah, so some connection issue, I think. So right now you can see everything is running fine with printing out the training accurate, the final test accuracy and the loss value. And also this the performance is pretty good. So if you are interested, you can compare like the bflow 16 recipe and also the FP 32 recipe. You will see the performance gain, and also you will get the same test accuracy at the end. So as a summary, so you can see this everything from the whole code. Basically, I think the only thing you need to change is set the global policy being mixed bflow 16. So this is the only thing you need to change to enable the bflow 16 on your Gaudi run. So with this, you will get performance gain without much additional effort. So this is the Keras way of enabling the bflow 16. So we also provide some like more finer granularity control on how you can enable bflow 16. So the second way, what we can do is using the JSON file to enable mixed precision. So this is shown, you can find the detailed implementation in this website. Go to this. So this website here, you can see on this model reference GitHub and the TensorFlow common bflow 16 config directory. You can find the JSON files we already provided. It has a basic JSON, BERT JSON, for JSON, transformer JSON, and the unit. So the basic JSON, that means the very basic ops that can be converted from bflow 16, FP32 to bflow 16. And for other, so the basic JSON is the most fundamental one. So that is safe for all the models. Safe means it guarantees the numerical stability for all the models. But for specific models like the NLP models, you might want to choose the BERT JSON. So that will have more models converting from FP32 to bflow 16. So if you look at into this JSON file, it has a few lists. So it has the allow list and the conditional list, and also the non-convertible exceptions, convertible exceptions. The ops in the allow list, that means those ops are general, is for sure it is safe to convert from FP32 to bflow 16. So that means when you go through the ops in the TensorFlow model, whenever you saw this op, it will convert it from FP32 to bflow 16. So for the op list in the conditional list, so that means it might have some exceptions, so that will be can be converted from FP32 to bflow 16. So this means this convertible exceptions always combined with the conditional list. So that means those ops will be like if you have such pattern match, so it's like it shows up in the encoder layer, attention self adds. So under this condition, it can be converted. So for other conditions, it will not. And there's the non-convertible exceptions. For those ops and patterns showing in this list, that means that those ops must stay in FP32. Yeah, so as you can see, we did provide these examples, like so for the BERT, so that stands for most of the NLP models, and the unit is for segmentation models, and the for JSON, that is the most aggressive way of converting the ops from FP32 to bflow 16, and also it is has the most complete op list. So you can add this for JSON in your run script and in your model script to have the fine control on what kind of conversion you want to have. So that is the example for the mixed precision enabling. So next, so I want to show you with the real training model that we can apply some additional optimization strategy. We will take the mobile net V2 as an example. The mobile net V2, it is a general mobile architecture that is based on inverted residual structure and linear bottlenecks. So that is that part of the structure architecture part is different from resonant models. It is parameter efficient And also it improves the SOTA performance of mobile models on multitasks and benchmarks, as well as across different model sizes. And it is usually used as a feature extractor to object detection with SSD and to the segmentation models with mobile deep lab v3. And for more details about the model, you can refer to this paper and also blog. So for all Gaudi, we support only TensorFlow 2. So if the model is originally from the TensorFlow v1, we need to manually convert the TensorFlow API from TensorFlow 1 to TensorFlow 2. So we either needed to get, so for the deprecated API, we needed to find the replacement, or we have to comment out for those tf.contrib that are no longer available in TensorFlow 2. So after the API converting, what we needed to do is just add the 2 lines to the model, load the Habana module, and also disable eager mode. So disabling eager mode, that is improve the performance. So the graph mode always has the best performance on Gaudi. MobileNet V2 can run a few different data sets. So in today's demo, we will show you with the ImageNet data set. So after you have the models running on Gaudi, so I think you might already know how to check the performance using the profiling tool. When you have the model running on Gaudi, so the most normal the performance issue maybe comes from the output placement on CPU. So we so as the Gaudi software, the Synapse AI software getting more and more mature, we do have more and more ops support on Gaudi, but still for some corner cases or from like a special usage, some ops might not be supported on HPU yet. So for those cases, it will fall back on CPU. So if you encounter those issues, so I think first you want to confirm how your op is placed. So it's on HPU or CPU. So TensorFlow does provide the default flags. You can check the op placement. For the HPU specific, we provide 2 additional flags. So you can enable this HBMTF graph dump equal to 2 and specify the directory you want to dump your graph. When you adding these 2 flags in front before your run command, you will see the output placement file generated as the Habana post placement 00 before pptxt. In this file, you can see the output placement, whether it is on CPU or HPU. So for if you have like a special usage or some special ops, you might see HPU does not support it. So for those kind of cases, you can either like ask Habana to support it. And if you want to explore by yourself, we will show you how. This is the op we found in the very early stage in our software stack. We found, hey, there's a few missing ops in MobileNet V2, and also our performance is bad. So we will show you how we improve the performance step by step. So the op missing the output placement on CPU does affect the performance a lot, actually. So even we only have one ReLU 6 op in the forward pass, put it on from CPU to HPU, we will see more than 1.7 times the performance improvement. And after we implementing the backward op as well, so it gives another 2x improvement. In total, we basically only these two ops, the ReLU 6 and ReLU 6 grad, we will gain more than 5x performance just placing this op from CPU to HPU without any further optimization. So the reason why the op placement on HPU is so important is the op placing on CPU, it breaks the graph, and also it make the data copy, extra data copy from CPU to HPU. So any data copy from the host to accelerator will produce additional cost in the training stage. So yeah, so basically we will show you, so if you encounter this case and you do not want to wait to implement your op or kernel, so you can do it yourself. So this is a very advanced way like to further optimize your own model. So here Zhongkai will talk about how to implement TPC kernels to optimize your model.
Okay, so let me start sharing. Okay. So hello everyone, and my name is Zhongkai Zhang, application engineer at Habana. So today I'm going to talk about how to write the custom TPC kernel. Use the example we provided in the GitHub repo, and how to place the custom op to HPU using the custom kernel we created. So first, let's talk about what's the TPC kernel. So the TPC kernel was designed to support deep learning training and inference workload. So we have 8 TPC core integrated to every Habana processor. So they were designed for customization, and they were fully programmable via AW4 DSP core for workload that do not map to the MME, which is the matrix multiplication engine in our TPC, in our the Gaudi. So Habana provides extensive kernels library, so more than 1,600 kernel library to enable the workload and the operator to be implemented. So VL AW4, which is 2048 bits, the SIMD. So it has a 4-stage pipeline. It has 4 slots: load, scale up, and vector up, and store to the memory. So this is the stackless, so we don't have the stack to worry about. So the TPC architecture takes advantage of 2 major characteristics of the workload. So operations can be vectorized and workloads can be processed in parallel. So next step is I want to talk about how to create the TPC custom TPC kernel. So first we need to install the Habana tool, so which include the TPC compiler, assembler, and the simulator. Next, we write your own kernel code using the TPC intrinsic. So we have the TPC intrinsic documentation in the Habana developer website. The next is the glue code. Glue code basically just a piece of code that set up the kernel's parameters and load the binary to the graph compiler. The last one is last but not least, there's the unit test, which is optional, which is you can use the simulator to verify your correctness, the correctness of the kernel. Then you can use the CMake list we provided to build the TPC library and compile to get the shared object. It's called the libs customer TPC perf lib This is include all the customer TPC you created. Then we are going to use this lab to integrate into the TensorFlow model. So let's take a look at the GitHub page to see what's the kernel looks like. So the first, this is the GitHub page for the customer kernel. So we have the README file. You can go through the detail to find out how to install. First, install the Habana tool. We have the Habana Vault, which has all this Habana tool. So we have regular release to make sure you get the latest one. In this case, you just use this command to install the tool. So after that, you can see this this tool we just mentioned before, and you just use the create your own build directory and use cmake and make to get the object. So the first, let's take a look at the kernel. So in our case right now is we use Relu 6 as a custom app. So first take a look at the Relu 6 forward kernel. So in each kernel, it starts with the main function. The function, main function, which has some argument list. So it always starts with the input tensor and the output. And if you have the accelerate tensor, you can put after that. And I think the scalar parameter is to follow that. So in each kernel, we start with some global function to get the index space. We get starting point and end point. Each index space is has a 4 dimension. Basically, it's follow like the first one is depth, width, height, batch, and the fifth dimension. Yeah. So we basically had the 5 loop to go through all the item inside the tensor. So in this Relu 6 forward, it's pretty straightforward. You can see the first we load the tensor. The last one is restore. So in the between, basically some of the logic is based on the op. So all this intrinsic you can find in the documentation in the developer website. So that's the forward. For the backward, the kernel will pretty much follow the same way. But one thing I want to emphasize is if you have the gradient tensor, you need to put in the beginning on the argument list. Yeah, that's really important. The same thing follows see all this load and logic and the store the final result. So that's the kernel part. Yeah, it looks pretty straightforward. So next part is also important. It's called the glue code. So for example, in our case, it's called Relu 6. So inside the glue code, we have 2 parts. The first one we call the get kernel name, which basically just get the GOID of the kernel. And the main part of glue code is called get the GC definition. So just I mentioned before, the glue code basically just set up the kernel parameter. So the first one is we validate the input. We basically check the data type and the size of the input and the output. And the next, we define the index space geometry. So we give the size. And also the third one is define the index space mapping. This is very important because this one is going to set up how the TPC core run the kernel. Yeah. So we basically give the starting point, end point, yeah, and for all this input and output tensor. So if you have some scalar parameter, you're going to add here. But in our case, in the Relu 6, we don't have anything. So we set 0. The last part, we basically load the ISA file. In our case, we have 4 different kernel. We have the Relu 6 forward, backward, and FP32 and BF16. Yeah, so let's conclude the glue code. So those 2 parts, kernel and glue code, are mandatory. So if you want to make the kernel functional, you need to have those 2, right? The last part is the test. this unit test, yeah, if you don't want to, unit test basically just test you, make sure, verify the correctness of your kernel, yeah. So inside this Relu 6, the first thing you need to write own reference code. So based on the logic of this app, you write your own reference. This one is going to compare with the kernel output. So the main test part is this run test. So in this case, so you need first set up the input and load this the tensor to the GC descriptor. The descriptor is going to be the input of this kernel, this Habana kernel, which is the glue code. So then we run we call the simulator, then to get the kernel output. Then you compare the kernel output from the simulator with the reference you just written. Then you will check it's going to fail or it's pass. So yeah, so this one is, I think, that the baseline for you to check the kernel's correctness. The next step, if you want to check, it's you can just write in the Python, use either TensorFlow or PyTorch, right? You can check the output from there. Yeah, but this one just give you the baseline. So yeah, so basically that's the kernel part. Yeah, I can show you in our system. I need to let me log into our system. So here you can see I already this is the Habana tool I just mentioned before. I already installed this tool, and this is the Gaudi tutorial, which is the let me see. Okay. Oh, okay. Actually, here, workspace. That's the Habana kernel. I just you can clone yourself. Yeah, I already cloned that. You can see here. Let me show you. Yeah. I already create the kernel. So inside the build, so after finish building, you can see there's called the libs custom TPC perf. This is the shared object you're going to use for the custom kernel. Yeah. So you can see here the test. Forward 32. You can see, yeah, this test is passed. Basically, they tell you this is the just a few output of the kernel. This is the output of your reference code. We can also test another one for the backward. Okay, so that's the kernel part. So next, I'm going to talk about how to place the custom op to HPU using the custom kernel you just created. So first, we already implement the kernel and the glue code. Then we create this object. Then the next step, you're going to set this GC kernel path and make sure you add this object before the default kernel. Otherwise, yeah, the default kernel could overwrite your one or you cannot find. So the next step is register the custom kernel to TensorFlow custom op. We also have the GitHub page to provide this example to how to run, how to register and build and use the custom op step by step. Yeah. The first should register this Relu 6 op and the Relu 6 grad op. And the next, just use the CMake list to build this binary. It's called the HPU custom Relu 6 op.so, which only contains just one Relu 6 custom op. compared to this one, the custom TPC perf lib, which include all the custom kernel, but this one only contains just one op. Then you can load this op into the TensorFlow kernel library and use it. Yeah, let me show you here in the GitHub. So in this README, we also have the link to direct go to this TensorFlow app example. So here you can see, so this example is it only has two files. The first one is the ReLU6 app. So inside this registration, we can call that, is we're going to register ReLU6 forward and backward to the custom app. So first we use this macros register app. We have those two app register, and the next one is just write your own the customer ReLU6 functor based on this base functor to register your ReLU6. We actually use the customer ReLU6 forward, and the same thing for the backward one. And the last one is the register kernel builder. You run this to register the custom op. So after that, you can use this command, and you just basically build to create the custom op. So we have the patch to show you where you can load the custom kernel. So in this case, you can see here, after we finish building, we'll get this custom ReLU6 app as SO file, and we load into the custom app lib. Then later on, basically in this model, we just replace all this CPU kernel, the CPU app, use our custom app. You can see pretty much everything will be replaced. Yeah, so let me show you here. So you can see here this is the custom kernel, and I already copied the TPC kernel lib here. So the first thing we need to check is we need to have this GC kernel path. Make sure this environmental variable contain this lib. So if you check that again, you can see the first one is the customer kernel lib. The followed by this is default one. And we also need to, okay, actually we need to go to the Docker. I already have the Docker running, so now we are inside the Docker. We need to, since the model needs to run inside the Docker, so we need to make sure this kernel path is set inside the Docker. Then we need to set the path on path. So that you can see here. The flow, or not this TensorFlow. We use staging. The flow. Okay. So that's the actual model. So we already have the data sets preloaded. So we can just run this command, see here, to start the training. The demo mobile v2. Yeah, I think now it's running. As I showed you before in the patch, we already replaced the custom op. Yeah, I think that it's running right now. And I think I can just hand over to Jianying to talk about the rest. Yeah. It's going to take a while to finish.
Okay.
Jianying, yeah.
Yeah, let me share my screen. So could you
let me start sharing. Okay.
Okay, thanks.
It's already running right now. Yeah. Okay.
Okay. Yeah, so right now, so you know how to implement your own TPC kernel. So for all like MobileNet V2 model, so right now we have all the ops running on HPU on all the training ops, let's say. And also let's combine the two optimization strategy, the mixed precision and the ops placement optimization. So let's take a look at the final run. So I want to show, let's see here. So I want to show you the final run result. So again, this is on the AWS DL1 instance. So this is the Docker setting. After this, we check out the model from the GitHub using this git clone. So it will download from the public repository. And right now we need to set the path to run MobileNet V2. Let's see. Okay, and I need to pre-install requirement. The final run command. So this is the final run command. So we specify the data type being bfloat 16, that is the mixed precision. Okay, it will run. And also let's look at the profiling information. Here we go. So yeah, this is the printout. My computer is frozen. Yeah. So I think through previous webinar, you already know the tool, the HLTV. So let's look at the final profiling. So you can see the top level here, the MME, this is the TPC. So this is all the two major Gaudi engine. So you can see this is the pipeline is very well aligned. So you can always zoom in. So if you want to get more detailed information. So since the two. Oh. So the zoom in, you can click like whatever the interested information from. It will report the details like the time, the duration, the detail, the op name, and such. So let's finally examine the performance. So you can see, so we only run it 500 steps just for the time constraint. So we did get like the original starting point is more than 2 seconds per step. So right now, our final performance is about 0.8 seconds per step. And the profiling, it shows also the good performance features. So as a summary, we achieved the excellent performance by combining the mixed precision and also the op placement strategy that is through the TPC kernel. And for the more details about this model, you can find in our model guard, the model reference GitHub. So we showed you the 2 key optimization strategies, the place training ops to HPU through custom kernel, and also apply suitable mixed precision recipe. So this optimization strategies not only applies this model, it applies to all the TensorFlow models and even applies to other frameworks like the PyTorch currently we support. So that's it. Thank you all for your attention.
Thank you. So we want to go ahead and open it up for any questions. At the bottom of the screen, you will see a Q&A. So if you could go ahead and type any questions that you have, and we'll have Jianying and Zhangkai answer those for us. Okay, this is, what are exactly the glue codes for?
Okay. So for me, I think the glue code basically just glue code is different than the kernel itself. It's run on the host, so not on the Gaudi device. So glue code is basically just side away to check the kernel input and output, and load the kernel and set the proper index space. So this, yeah, that's the reason we call the glue. Yeah.
Okay.
Basically, it's property setting and the checking. Yeah.
All right, let's see. Is a custom kernel required to get good performance on a HPU?
No. So the customer kernel implementation is a really advanced feature. So that means you want to write your own kernel. So for example, you might think, for my special case, the default kernel does not work as efficient as my own algorithm. So under that case, you might want to use your own, write your own kernel. So as each release for our software stack, we have more and more support of the ops. So I think for most of the cases, you will see less and less cases you have to place your op on CPU. So this is really advanced feature for advanced users. So you want to really refine your performance by your specific algorithm and also really special usage case.
Okay, let's see. Do you support the latest TensorFlow version and Keras models?
Yes. So we normally support for each release, we always support 2 TensorFlow models through two TensorFlow model window, let's say. So for example, last release is in December for us. So that time, the latest TensorFlow was 2.7. So we do support the 2.7 TensorFlow version and also the 2.6.2. So for next release, we will depend on what is the latest TensorFlow. We always support the latest available TensorFlow and the one before that. So for your models, so as long as it's TensorFlow 2, so it should run with those latest TensorFlow versions, and also it supports the Keras as well.
Okay. Where can we find more information on TPC Intrinsic?
Yeah, I can post the link. So I mentioned that in Habana.ai, we have the developer website, and there's some documentation. Yeah, I can post the link, and let me find it out. Yeah, okay. There's basically all this the intrinsic, and you can check all the detail there.
Okay, and then there's another.
Let me post the link here.
Perfect. There's another question for you. Is there a difference to write the forward and backward kernels?
Yeah, I think just I mentioned before. So the forward and backward, and the only difference is in the backward kernel, you need to make sure if you have the gradient tensor, you put the gradient tensor in the beginning of the argument list. Yeah, so that's make sure the Graph compiler can find it out. I think that's the only thing you need to make sure that's correct. Yeah. But also the logic, they follow the own logic. Yeah, that's it. Yeah.
Thank you for that. We are reaching time, so if you have any other questions, you could either email us or go to our forum to ask it. So with that, I want to thank our presenters and also thank you for attending this webinar. Please do visit our developer site for documentations and GitHub for model examples. You can access Gaudi on Amazon EC2 DL1 instances. And for our on-premise solution, we have partnered with Supermicro. Please visit our website, habana.ai, for more information on that. Our next session is scheduled in 2 weeks on Tuesday, February 22nd. Again, it's at 9 a.m. using the same link. Please mark your calendars. In the meantime, again, if you have any questions, please go ahead and go to Habana forum to post your questions there. Thank you again for attending, and we look forward to seeing you in 2 weeks. Thanks, guys.
Yeah.
Thanks.
Thanks very much. Okay. Bye.
Bye.